This demo is all about how user-defined functions can affect the ability for our Spark jobs to run in an optimized fashion. I've gone ahead and run all on this notebook so that we don't have to wait for cells to finish executing. And we're going to talk about how these user-defined functions, or UDFs, can honestly just drastically slow down your queries. I've run the classroom setup, which has defined my schema and my data sets, and let's get into it. I also, just like in the last two demos, I've disabled caching just to make it a fair fight. And I'm generating data. This time, this is going to be just some telemetry data, essentially just some readings that might come from some device or another. And I'm only doing 60 rows. You'll notice here now that 60 rows is not a lot, but you'll see how this is going to work as we get further into the demo. So I have an ID, I have some device ID, and then just some temperature reading that's been made up. And notice that it is in Fahrenheit, and I get it the American way. I would love Celsius. Let's actually convert this to Celsius, right? Because I'm not a big Fahrenheit fan. But we've written this out to device data, the table called device data. And let's just say, for example, we're going to make this computationally expensive UDF. And we're going to use Python to do this, right? So the idea behind this now is that maybe this computation, f minus 32 times 5/9, is not really that computationally expensive. But let's go ahead and add a 1-second delay in this so that every time it executes, it takes a second longer, just so that we can see how this affects the running of our query. So essentially, we're just defining in Python now a UDF that's going to be a double, right? So we've defined f to Celsius now. It's going to accept one parameter. We'll call it f. We'll have a delay of 1 second. And we're going to return f minus 32 times 5/9. And then let's actually use this now. We're going to capture our output as Celsius df. We're going to call table on our device data, right? Data that we synthesized up earlier. With our Celsius column, then we're going to call f to Celsius, passing our temperature f column as the data that is going to be input into this function. And then we will return it and call that column Celsius. We'll then overwrite our table Celsius, saving the data that we've returned now as our Celsius table. So if we look at this now, how long did this take? All right, let me mouse over this. We've got 1.05 minutes. Okay, so wait, what's going on here? So if I look at my cluster up here, I can see I've got 4 cores on the cluster. So I should be able to parallelize my 60 rows of data. But if each row takes 1 second, then that's where my 1 minute comes from. So obviously I have not parallelized my 60 rows of data. I've essentially executed them concurrently. Why does that happen? And I'll tell you the reason why is because Spark has no idea that our function here is computationally expensive. And so it doesn't partition the data, push it out to different executors, different cores, and say, let's go ahead and parallelize this. It just says, great, let's go ahead and run these data through this function. We'll get the return results. We'll write them out to the data frame. We'll be good to go. What we have to do is that we actually have to explicitly tell Spark, go ahead and partition this data. We want to make sure that we parallelize. So what we do here now, we're going to specify a variable called number of cores equal to 4. And that's specifically because this particular cluster has 4 cores. If you have a different cluster, you might have the number of cores be different for that different cluster. Everything else is the same, except that when we actually run our data through this function, we're going to specify with a dot repartition and pass the number of cores into this repartition. What that's going to do now is that Spark is going to say, oh, okay, let's go ahead and repartition or partition this data into 4 batches. Let's send it on out to all the executors. They'll get a copy of the UDF, and we'll go ahead and run that data through that UDF. We'll be good to go. Now, this does still take time, right? Because it's a Python UDF, the data still needs to be serialized. The expression itself, right, the function itself needs to be serialized and pushed to those executors, which is, it's not nothing, right? It's still going to take some time, but it's certainly going to be better to take advantage of the parallelization that's inherent in the cluster that we've chosen. If we look now at the Celsius data frame and we call .explain on it, we can see that we have our round robin partitioning here equal to 4, or that we have 4 in this because that's the number of cores that we have. Now, I do want you to note now also in this explanation that we are not able to use Photon, right? And that's because, as it says here, it's an unsupported node. Essentially, we are repartitioning. What it boils down to is we're using Python. That's the key to it. So how can we fix this even more? Let's look at redefining this function as a SQL UDF as opposed to a Python UDF. The reason why is because SQL UDFs don't require data serialization, like we talked about earlier. And furthermore, we can take advantage of the Catalyst optimizer that can work with SQL UDFs. Let's see how we can redefine this function now. The exact same output, the exact same function, but written in SQL. We're first we'll drop it if it exists, and that's just so it's idempotent. We can run it again. We'll create a function. We'll call it a far h to cells. It's going to receive a double. We'll just call it far h. It's going to return a double, and we'll return now, here's the logic, far h minus 32 times 5/9, and it's done. Let's go ahead and then create a table or replace, again, just so it's idempotent. We'll call it Celsius SQL as select, and then here's where we actually use the function. Far h to cells, we'll pass in temperature F, and we'll call it far h to cells convert from our device data table. How long did this take? It took a lot less time, and I get it that there's no 1 second delay in here because we didn't induce a 1 second delay, but 3 seconds, that's pretty fast. And let's look at what happened now. We see the results are the same. It's all good. Celsius SQL has the exact same results as what we had up there. But let's go ahead and explain now the query plan, the physical plan that was involved in this. We can see that it has the same function that's involved, but check it out. We've got Photon. The query is fully supported by Photon, and so Photon's able to be used, which runs things faster. SQL queries are faster, and we have that optimization that's built in through this process that makes everything much faster. So what it boils down to is, if you need to use a UDF, write it in SQL if you can. I'll tell you what, try and use the built-in functions if you can. They're going to always be faster. They're already optimized. If you need to use a UDF, write it in SQL if you can. If you can't write it in SQL, for whatever reason, it needs to be written in Python, then certainly talk about and tell Spark how to repartition the data based on the cluster that you're currently using. And finally, if there's no way around it, then you're just going to have to deal with it, and it's going to take a little bit less or a little bit more time because it's going to be less optimized.